Hi, I'm Chris, and today I want to show you how you can use ropenlib to oversample your oscillator designs. I have just updated ropenlib today with separate up and down sampling algorithms that you can use to upsample a signal, so produce more values at a higher sample rate from one sample at your base sample rate, or downsample, so take multiple samples at a higher sample rate and downsample it to one sample at your base sample rate. This is the IAR downsampler. It implements the RI downsampler interface. We need to use this interface to be able to switch between different types of downsamplers. For now, there is only an IAR-based and infinite impulse response-based downsampler and upsampler. These are not linear phase. They are reasonably minimal phase, but they are very efficient compared to FIR-based up and down samplers that can be linear phase. These will come in the future, but for now we have the IAR up and down sampler and oversampling modules in ropenlib. We also have the no downsampler that implements the same RI downsampler interface that just passes the values through as they are passed into the downsampler. This is added for your convenience, so you can use a downsampler in your processing routine, and if you have no oversampling, or in that case no downsampling of your oscillator, you can still use the same code. You just need to switch the actual downsampler with the no downsampler and you're good to go. There is also the upsampler, which is new, which does the same as the downsampler but in the opposite direction. It has the same interface. It has almost the same interface. It only has the process function that takes one single double value and produces an array of values. The downsampler actually has two process functions, one that takes an array of double values. It is expected that it is one value per oversampling factor. So if you have an oversampling factor of 2, it expects 2 values in this array. And if you have an oversampling factor of 4, it expects 4 values, because these 2 values at double the sample rate will be converted to 1 value at the base sample rate, and the 4 values at 4 times the sample rate will be converted downsampled to 1 value at the base sample rate. For convenience, there is the RI value generator interface, and if your processing function, your processor, your oscillator, whatever you need to downsample implements this interface, you can directly put in the generator into this process function, and the downsampler will take care of calling the getValue function that's specified by the interface once for every oversampling step. So again, if we have an oversampling factor of 2, the value generator getValue function will be called twice. So in case of an oscillator, we would typically advance the phasor, the phase accumulator, once per sample, and we would implement that in the getValue function and also the calculation of the signal. And this would be done twice at an oversampling factor of 2. And this also means that you need to take care of setting everything according to the sample rate that you want your processor to run at. So in case of an oscillator, you would need to set twice the sample rate if you want to oversample 2 times, and 4 times the sample rate if you want to oversample by 4 times. Speaking of oscillators and downsampling and oversampling oscillators in general, let's jump into Vim to look at an example. I have provided an oversampled oscillator example. It's a naive implementation that is not to be taken literally. It's just a showcase, a tutorial of how the oversampling would work for your own oversampled oscillators. As usual, all you have to do to be able to use ropenlib is import it. And we do that in the user import section with the import command. You have to specify import com.our.ropenlib.roversampling.star. And this star the end, this one here, means that it will take every content of the oversampling package, so the RI downsampler and the I downsampler interface and the I value generator interface, and make it available in this file. Okay, first of all, let's take a look at what we actually use. And here we can see we have several member variables in our module. For the downsampling, we basically only need this. It's an instance of an RI downsampler that I called mDownsampler. And this variable will be an instance of RIR downsampler if we enable oversampling, or R no downsampler if oversampling is disabled. We have an oscillator. I typed out a quick example of a very bad oscillator. Please do not use this. This is just an example. This oscillator aliases like crazy because it's a naive implementation that does not handle the discontinuities in the saw and square wave that it produces, but it serves as a great example to show how oversampling minimizes the aliasing that is produced by this not band-limited oscillator. If you were to implement a real oscillator, you would need to band limit it by means of polybleb, for instance, or a minimap wavetable based oscillator, and all that jazz. But for the sake of brevity and to keep this example short and to the point, it's just naive saw down here, saw value, and a very naive square that's based on the signum function here. Okay, before we talk about how the downsampler takes care of oversampling the oscillator, let's quickly go through this oscillator class. This oscillator takes the sample rate and calculates the sample rate reciprocal. So it's 1 divided by the sample rate. We need this for the phase accumulator, or the so-called phasor with an O, not an E. It's not a phasor, it's a phasor. It's basically just a ramp up wave that drives the signal generator. And the increment per sample is based on the sample rate and the frequency. And we can see that here in the set frequency function. In this basic implementation, we can only put in positive frequencies because the oscillator is not equipped to handle negative frequencies. It is not even limited. So if you input negative frequencies here, it will literally break. But I digress. The phase accumulator increment is calculated by multiplying the frequency with the sample rate reciprocal, or more simple, by dividing the frequency by the sample rate. I chose to multiply with the pre-divided sample rate and remember that value as sample rate recip in order to save processing, because division is a very costly process, and we can save some CPU cycles by calculating the division beforehand. We will not set sample rate once per sample. We usually do that when we instantiate the oscillator or when we change the oversampling, and that happens spontaneously but not periodically. So it makes sense to offload the heavy processing to these times. But the set frequency function will be called once per sample. So we want to be as efficient as possible in this function, or in functions that are called once per sample or are called often. Once per sample, we need to call the advance function. That's how the oscillator works. The advance function will calculate the current values for our saw wave and square wave, and will increment the phase by the phase accumulator increment, so the value that's based on the current frequency and the sample rate, and then it will wrap the phase in the range of 0 to 1. I do that with this neat little floor trick. By casting a double value to an integer value, you basically floor the value very efficiently, and if I subtract this floored value from the initial value, I can wrap in the range of 0 to 1. So for instance, if our phase, M phase, has a value of 1.1, casting to integer will result in a value of 1. And if I then subtract this value of 1 from the initial 1.1, I will be at 0.1 again. So I've successfully wrapped in the range 0 to 1. We implement the I-value generator interface with this oscillator, and all that we need to do for that is implement this getValue function that advances the oscillator and returns either the saw wave or the square wave value based on this little Boolean value that we can set. Okay. So initially, in our initialize function, we of course initialize our variables and objects. And initially, the oscillator is set up with the base sample rate of 48 kilohertz. Now, this is, luckily for us, stored in the values.sampleRate constant in VMD that we can use. We also assume that at the beginning there is no oversampling, so I instantiate M downsampler to a no downsampler. However, there is a switch on the interface that sets the oversampling factor at the leftmost position, so at its value 0. The oversampling factor is 1, so effectively no oversampling, and then it steps through powers of 2. So 2 times oversampling, 4 times oversampling, 8 times, and 16 times. For each oversampling factor, I need to set the sample rate in the oscillator accordingly, so that the phase increment gets calculated based on the new sample rate. We can make a quick detour and have a look at the set sample rate function. So I reset the sample rate increment by multiplying it with the sample rate so that it's converted back to frequency. I set the new sample rate, calculate the sample rate reciprocal, and then calculate the new phase accumulator increment. That's all. And the next time I set the frequency, or next time I advance, the new value of M phi will be taken into account. And also the next time I set frequency, the new value for our sample rate reciprocal will be taken to calculate the phase accumulator increment. Okay, if I have no oversampling, so an oversampling factor of 1, I can set the, or I can initialize my M downsampler variable to a no downsampler, which just passes the values through unchanged. But if we have oversampling, I need to set up an RI downsampler. And in order to construct an RIR downsampler, I need to pass the current base sample rate. For now and for the foreseeable future, this will always be 48 kilohertz, because that is the sample rate that Voltage Modular runs at, regardless of the host sample rate or whatever sample rate is set in your sound card. Voltage Modular always runs at 48 kilohertz. Again, lucky for us, this constant holds this value, so we use that. We then set the oversampling factor that is given by the switch position, and we set a cutoff frequency. In this case, I decided for 20 kilohertz. The cutoff frequency is needed because we need to filter the content, the frequency content that would theoretically reflect back when we downsample to our initial sample rate. And the frequency content that reflects back is that is above Nyquist. The Nyquist frequency is the half of the sample rate and is the frequency, or is the highest frequency that we can produce without aliasing. Since a saw and a square wave have lots of high frequency content, and especially if you do not band limit them, they will naturally go way above the Nyquist frequency. So our downsampler effectively increases the Nyquist frequency, or the oscillator basically has an increased Nyquist frequency because we set it to a higher sample rate, and then the downsampler removes the content that would fall back at the base sample rate and then downsampled that band limited signal to one sample at our initial sample or our base sample rate. That's how it works. And in the process sample function that gets called once per sample, it's very simple. We just need to call the process function of the downsampler. And since we implemented the RI value generator interface, we can pass the oscillator directly into this function so that the downsampler takes care of advancing the oscillator and getting the values it needs for the downsampling. We then get one sample at our base sample rate that we can output. The alternative way to do this would be to call the advance and the get value function of our oscillator manually for the given oversampling factor and create an array that holds the values that are produced by our oscillator at the higher sample rate, and then give that array into the process function of the downsampler so that the downsampler then takes all of these values, downsamples them to the base frequency, base sample rate, and gives us our output value at the base sample rate. But less code, less errors. So let's have mDownsampler do all the heavy lifting and just input the oscillator. That's all you need to do to oversample your oscillator. Now let's have a look at Voltage Modular Designer, where we have the actual module that's implementing this oscillator, or that is the implementation of that oscillator that we just saw the code of. We have the oversampling factor switch, we have a frequency knob, there is not even a frequency input, it's just a very crude example. We have a waveform selector that we can select between saw and square wave to see what the oversampling does to these waveforms, and we have an output. Let's switch to full screen. All we need to do in Voltage Modular Designer to be able to use the downsampler is include the downsampler interface, the IIR downsampler implementation, the no downsampler implementation, a resample filter interface, the actual resonance stacked resampling filter, and the RI value generator interface. We need all of these files to be able to use them in Voltage Modular Designer or in the code that we then put through Voltage Modular Designer. Now let's have a look and have a listen how our naive oscillator sounds and what the oversampling does to this implementation. Okay, we can see our square wave that is produced by our oscillator. It's a naive square wave. That's why we can already see lots of reflected frequencies, lots of sidebands, inharmonic sidebands. All of this that is in between our harmonics, this is aliasing. If I now increase the oversampling factor, we can see the characteristic cut at 20 kilohertz. That's a dead giveaway for oversampling, by the way. So if you have a plugin or a processor or anything, and you notice that somewhere around the Nyquist frequency it has a steep cut, that's oversampling. Oftentimes. We can see, and to my ears I can already hear, that some of this aliasing buzzing is gone. It might also be the filter that's taken away some of the very high end, but we can clearly see in the spectrum. Let's compare that again. Not oversampled. We have, let's take this as an example, minus 40 dB sideband here at 450 Hertz. That's sticking out. And if I oversample 2 times in the range 400 Hertz, we now have minus 46 dB as the highest aliased sideband. oversample 4 times, and we see another quality improvement 8 times, more quality improvement, and 16 times. And it's a reasonable oscillator. It's still a very, very bad oscillator, don't get me wrong. But if you only intend to play bass notes, this might be acceptable for a lo-fi synth oscillator. But yeah, as we clearly can see, no oversampling, lots of aliasing, 16 times oversampling. It's a lot better. And the same is true for the saw wave. Saw wave also has a lot of reflective frequencies, and if I increase the oversampling, instantly better. Once again, even more better, better, best. That looks a lot better than no oversampling. Now let's turn off the volume and increase the frequency. The higher the frequency, the more harmonic content will be pushed over the Nyquist frequency and fold back. And that's what we can see very clearly here. We can see at Nyquist, that is the red line here, that the frequency spectrum is reflected back into the audible spectrum. That's how aliasing is produced. Or that's the reason for aliasing. Let's keep that look here, and if I add 2 times oversampling, there's less, 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 and again less. See? Already a lot better. And of course, at higher frequencies, the aliasing will be worse. Oh, now I did a magic trick and removed all of the aliasing. That is because we're now at 2000 kilohertz and 48 kilohertz sample rate. That also works for our bass sample rate, by the way. No aliasing at all, because we do not have fractional values here. That also works for, let's say, 100 hertz, because our sample rate is divisible by the frequency without decimals. So this jump here is in fact no discontinuity at this frequency, as it can be, as each value is mapped to one sample. We do not have intersample values. Awesome, isn't it? But once I go just a little below, horrible aliasing. Oversample. Still horrible, but less. Okay, that's it. If you enjoy this content, if you want to see more of this content, please like and subscribe. And I hope you learned how to oversample your oscillators with the help of ROpenLib.